Luca, the stage is all yours. You'll have 10 minutes and then we'll catch up later on. Thank you.
Yeah, thank you very much. Thank you very much. Thanks for this opportunity. Just a couple of words about myself. I'm the founder of Spark.ai. We are a computer vision company based in Ireland. And today I'm going to talk to you about something I'm very excited about. It's called Generative Deep Learning for image anomaly detection. As you know, generative deep learning is gaining momentum, and it's not only about deep fakes, it's also about great applications in use cases like anomaly detection in manufacturing. So this is what it's going to be all about. Again, at Spark, we are focused on manufacturing solutions in different domains. I mentioned the computer vision, but we also look at other techniques, like for instance, object detection and tracking, health and safety. So there's an awful lot of things that you can do in this vertical with cameras and with computer vision. Today, we're going to talk about a very specific one, a very specific use case. This use case obviously implies an architecture based on cameras. You could have a RGB sensor, you could have depth sensors, or you can have both of them. The important thing is that these cameras and these sensors capture a production line where you have products that can be essentially, let's say, fulfilling all the quality criteria that your control lab pushes or not. So in this example, we are producing apples, and there are two different categories of apples: the apples that are passing all those criteria, and the apples that are failing maybe one or multiple criteria. So you really need in this case, a visual metric that tells you whether or not it's class A or class B. So in this presentation, what I'm going to share is some algorithms that are very, very helpful for learning in a very generative and very, let's say, abstract way what the anomalies look like from a visual perspective. In terms of benefits, if we do that, if we are, let's say, the promise is to have obviously an increase in productivity because with these visual non-intrusive metrics, you're really able to understand and spot where the errors come from. Obviously, there is also, as I mentioned before, new opportunities in the safety domain, because since you have cameras installed in your production lines, you can also use such cameras to detect events of interest. So here we're not talking about quality control specifically, but we are we're speaking about other use cases related to health and safety when your workforce is collaborating with robots. So there's an awful lot of things that can go on, and with cameras we're able to capture that. So there are synergies when you're deploying fleet of sensors like this. So, important thing here when we're talking about anomaly detection is to understand where the anomalous part of the image is. So here you have an example. You have a chip, and one of them, as you can see on the top left, has a bent pin. And the idea is that with cameras and with a certain type of algorithms, you're able to essentially detect and locate where the anomaly comes from. I'm not going to go too much into the details of the prior art because again, the interesting thing, what I would like to convey in this very few minutes that are left here is the technique, the most advanced techniques that are obviously based on deep learning. One of them is the autoencoder networks that I'm going to present here. Traditional methods of transform, sift, these are all features and classification algorithms that were used in the past. But let's have a look now at what we're using at Spark, which is called the variational autoencoder. We're very excited about this technology because it can be used in multiple scenarios, in multiple use cases. In this use case here, we are essentially trying to reconstruct an input that is corrupted by noise, as you can see here. The normally are familiar with the NIST dataset. This is a classic dataset containing digits. Here you can read 7210, and to make the story short, what we do with a variational autoencoder is to feed the autoencoder with a noisy input where all these digit images are corrupted by random noise. So the variational autoencoder is a black box that essentially gives as output the cleaned images. Now, in reality, this variational autoencoder is not a black box. Obviously, it is a network that contains an encoder and a decoder part. And what it does is it learns distribution of the data. This is brilliant because if you learn this distribution of your data, then you're also able to understand if there are shifts or if there are divergence from this normal distribution of the data. And this is at the core, this is the idea at the core of the anomaly detection algorithm. Let me give you an example. Here we have a brilliant dataset called MV-Tech that contains a lot of different images with different types of defects. Here you're looking at the bottom of bottles, and in this different variations of the same image, you can see that some of them have defects and some others have no defects at all. So for instance, in this image and that image, I will go back, you have defects. So the variational autoencoder essentially is able to take the input image, as we said before, and if you are careful, you can spot defect here and denoise the image. So it removes this artifact, it removes this anomalous part, and it gives you a clean image. So what do you do with the denoised image? Well, very simple. You add it or you remove it from your input image, and you get what we call the residual image. In this residual image, the defect is highlighted, as you can see here on the top. So in other words, the variational autoencoder learns the distribution of your data. It gives you a denoised clean image that then you will subtract from your input image. And in doing so, you are producing a residual image where your defect is clear, appears clear. I would like to stop here. I think I leave a couple of minutes for questions and comments. And thank you very much for your attention. And sorry again for the problem with the previous part of the presentation.
Yeah, well, thanks, Luca. That was very much spot on time. Sorry that you weren't able to finish this before. I think I didn't fully catch in which context you're applying this. Could you just outline that? I mean, or give a customer reference?
Yes, sure. So the typical use case for visual anomaly detection is on production lines, and we're talking about manufacturers or food producers. This is the key use case. Yeah,
and just to understand the technology stack you've been using, I don't know why, but I've now dropped off. It's probably working, having to answer in the background, but there he is again. You just have to mention things to people. Hi, there you are. And Thomas, we discussed, the technology behind this, right? Obviously, the technology enabling this is a very important part because it can make the difference between, doing this maybe in a 1 week project, a 3-month project, or making this a never-ending story. I mean, what kind of technology do you leverage? And I'm not sure if you were dropping in and out, how you heard the other two speakers, implementing MATLAB, obviously, the workhorse of the engineering students in the United States predominantly, versus the Merantix Labs solution, Kubernetes clusters and so forth. What do you think? I mean, what do you leverage?
It's a very multifaceted answer that I need to give because it really depends on the client. For instance, if the client has a private cloud requirement, so they don't want to use the usual APIs, or there is a bandwidth requirement, so the algorithm needs to be deployed at the edge, that's a completely different story. That's why at Spark we implemented a very flexible stack, and our preferred stack, the easiest to implement, is the one that implies an AWS server, probably even a Lambda if there is room for that, and the usual PyTorch That's again our favorite library when it comes to our cloud stack. And then for the acquisition part, again, it depends on the hardware of the client, unfortunately. So there is a lot of ifs.
Yeah, I see. That seems to be the state of the industry at the moment. There seems to be lots of ifs, lots of interesting solutions. I think we're yet to standardize this in a meaningful way, but I think there were some interesting approaches here. Time's already up. Unfortunately, I think that we lost quite a bit of time during the transitions, which is unfortunate. So hopefully with the next speakers already queuing up, maybe we'll have a bit more time there for Q&A. Thank you all for joining this morning. Right, I hope you're sticking around at the conference so that people can connect with you through the chat function on Hopin. And well, all the best with your endeavors. Best of success.